So let's go back to the model that we had for a BJT. For a BJT, the hybrid pi model was this. Collector, base, emitter, and we had IB going in. And this is an NPN, but again, they are very similar, NPN and PNP. And I have a bit of good news that I will tell you after this. So this is VBE, and this is either beta IB or IS e to the VBE over VT, right? And then if you go and attach a voltage source here, and maybe you use this output as a, let's say, just measure the current here. Use collector as the output terminal. This is the common node for now. So we're measuring the current here, IC. If you go and look at ICVBE, assuming the device is in active region of operation, ICVBE looks like this. Okay, assuming that your collector voltage is held above the saturation level for the transistor. Okay, so this was the input-output relationship for this device. We have biased it at some desired bias point, so it's sitting, let's say, at this point. So let's call this VBE naught and IC naught. Or Q, sometimes they use Q. Okay, this is my DC analysis. And now some small change has happened at the input. So my VBE, the small VBE has been added to my original signal, right? So I have moved from this initial bias point to some slightly larger voltage. So VBE naught plus delta VBE plus VBE, which is, VBE is some small change in the voltage. So I go from here to here. IC obviously increases, so IC I go from the original bias point to some new value. So I'm going to look at the small change in the IC. Hopefully it is small. I'm going to use the lowercase I and lowercase c to indicate the change in IC. So I've had a change in VBE, and it has created a change in IC. And the question is that how much is that change? So this is the new value for VBE. How much is this change? If I have this much variation in base emitter voltage and get this much IC variation, how much is it, right? It's the changes. It's the delta V in and delta I out that I'm showing as lowercase VBE and lowercase IC. And again, you can go and use the nonlinear equation, and we know how to do it the hard way. Let's use our engineering education here and then find an easier way of doing it. My engineering education tells me that in a situation like this, one solution could be to, if the changes are small, to go and approximate this curve with a line instead of dealing with a straight with a curve. I'm going to assume that this is a straight line. Well, I'm assuming an exponential is a straight line, so I'm going to underestimate the actual signal a bit, right? Okay, harder. Yeah, this is good. Okay, so I'm going to have this line here. Instead of figuring out, what is the nonlinear function and all that, what I'm going to do is that I'm going to find out this slope and say, okay, if I know that slope, I can go and calculate this height. If I know this delta VBE, I multiply it by that slope, and I get this delta IC. The issue is that I'm probably going to underestimate the true value of the change in the current, but if the changes are small, this is not a bad approximation. So let's go and figure out the slope of that curve at that location. So IC, I know, is given by this expression, IS e to the VBE over VT. I'm writing it as a signal that has both AC and DC components. If you want, you can add the one here as well, but as we said, for a device that is turned on, that's really small. So then I can see that, let's say IC naught plus IC, this is the DC plus AC component, DC plus the small signal component is going to be, IS e to the VBE naught plus VBE over VT minus 1. And same thing that we did in the above, we looked at the Taylor series expansion. We do the same thing. We bring IS e to the VBE naught out. So it's IS, let me just move it to here. So this is going to be equal to IS e to the VBE naught over VT times, and then the Taylor series expansion of the second term, the e to the VBE, so this part here, right? So this part, I'm going to write the Taylor series expansion for that. So it's going to be 1 plus VBE over VT plus 1/2 VBE over VT squared, and so on and so forth, which then I approximate with just these two first terms, right? So if VBE is small compared to VT, the higher order terms you can ignore. So it's going to be IS e to the VBE naught over VT, but I already know this is IC naught. So it's going to be IC naught plus the second term. Second term is IC naught times VBE over VT. Or if I want to write it in terms of, if I want to write the changes at the output, only this port, as a function of the changes at the input, I can see that IC is IC naught, the DC value divided by VT times VBE. Okay, so this is the slope. IC naught over VBE, IC naught over VT, that's the slope. If I know how much VBE I have, I can multiply it by this the slope, and I get how the change in the output current. But this is a very important parameter in analog electronics. We give it a name. This slope for a BJT, we call it GM, the transconductance of a transistor is defined like this. Right? So we went through the small signal, we used the Taylor series for a small signal assumption. This term GM is called the transductance of the device, transconductance of the device. And it tells you the slope of variations at the output. Now, so that I can go back to my model here and, redraw it a little bit. So what I can do is that I can go and say at the output, if I'm only interested in the changes, this part, if I'm only interested in the changes, I have a DC current source. Right, so this is IS e to the VBE over VT. And then I have an AC current source whose value is GM VBE. Right? And what are these two? Well, VBE is the DC voltage across the diode. So this is VBE plus VBE. And the capital VB is the DC voltage, the lowercase VB is the AC voltage portion. As I said, the whole goal here is to separate the DC and AC analysis from each other. So I'm going to get rid of the DC components. I'm going to focus only on the small signal parameters. So what I want to do is that I want to use this model that I see here for the DC analysis and establish my operating point conditions. After that, I want to focus on the AC analysis and small signal. So because I've dealt with that before, I'm just going to get rid of this part, right? And I'm going to get rid of the DC analysis here. What I have here is just a GM-VBE current source that converts the changes in the input to a current. Now, here at the base emitter end of this model, I also have to have a revision, right? There was a diode in there, and we saw that for a diode, and you look at the small signal variations, the diode is represented by a resistor. So if you go and have a diode, the resistor value that you used in small signal analysis was VT over ID. Okay? So NVT over ID for a diode, but we said, so let's just write it NVT over ID. For a regular diode, but we said for BJTs that N is close to 1. So I have to put that, because I'm dealing with small signal analysis now, and I'm not going to go through that. You can go back to the diode lecture to see how come we ended up with a resistor here. But the diode is represented with a resistor value. ID in this case, well, ID is IB. The current that is going through the resistor is IB. So the resistor value between base and emitter is VT over IB. Okay? Sorry, IB is the DC current, right? The DC base current. Well, okay, if I go back and use my equations, I know it's VT over IC divided by beta, right? IB was beta times smaller. So this is just beta VT over IC, okay? But I already have chosen a name for IC over VT ratio. This ratio already has a name. So RBE in this case, the resistor that I put here, is going to be equal to beta over GM. Okay, so you calculate GM based on the DC collector current, and you use that as a multiplier in front of that controlled current source. That same value, you just multiply it by beta and inverse it, and then you can use it to calculate the resistor that goes in here. So this is the resistor, this is VBE, and this is RBE. Okay. Now, if you look at this model, it looks like an inverted pi. This is called the hybrid pi model. This is the model that we use for NPN device analysis, and we're going to use it here. It is common to rename these variables here. So what we call this resistor is, we call it R pi, but the voltage drop across it is then called GMV pi. And sorry, it's called V pi, and then this current source obviously becomes GMV pi. So this is the hybrid pi model for the small signal operation of a transistor. And this is what I will use from now on in my small signal analysis, right? So if you give me an amplifier circuit that has DC plus AC sources in it, I'll take out all the AC sources, figure out where the device is standing in terms of DC operating point. Once I figured that out, basically once I figured out what is my IC, I go and calculate GM and also R pi, take the transistor out of my circuit, put this model in there, get rid of the DC sources, apply the AC sources. I will have a linear circuit now, very easy to analyze. You can see that in here I only have a controlled current source with the GMV pi and R pi that is again a linear circuit. So I go back to the linear domain. I do all my analysis with the linear circuit. Yeah, I may have a few, let's say, equations, KVL and KCL here and there to solve, but everything is linear. Everything is back to what I used to. And as long as my variations of base emitter voltages or currents are not too large, I should be okay. So I calculate my small signal parameters, look at the output. I will see some change at the output. If I need to, I can add the DC part to it to make sure that everything is fine. But usually, no. Because in most cases, you actually, for DC values, you have well-defined parameters. Your power supply voltage is, let's say plus and minus 1.5 volts. Those are given. They are not changing. Or plus 10 volts. And then you bias the transistor with a 1 milliamp current. And that's done. Once you choose your resistors and then establish the current, that's it. For the small signal parameters, that actually is not the case. That V in is coming from a signal source. So you really don't know what the amplitude of that signal is. You just know it is small. So it really is not necessary to add the small signal and large signal to each other most of the time, because the DC part has a well-defined component. AC part, no, it is variable, it is changing. Usually we talk about ratios for small signal quantities. Now, this, we started with an NPN transistor, which has a large signal model like this, and got to this small signal equivalent, right? So this is NPN. So this is VBE, and this is IS e to the VBE over VT. Okay. I'm going to make a quick comment here about the small signal analysis model for PNP transistors. For a PNP device, this is what we had. So the large signal model was a bit different. So what you had was an emitter at the top, right? This is your PNP device. So emitter at the top, base here, and a controlled current source over here. So this is your collector, base, emitter, IE goes in, IB comes out, IC comes out, right? So the model is different. So for the large signal behavior, this is VEB now, and this is IS e to the VEB over VT minus 1, which I'm going to just ignore. Okay? And then the question is that, okay, so how will the small signal circuit for the PNP transistor look like? I'm going to start it, and I will like you to just go and finish that discussion at home. So what we'll have is that, again, an equivalent circuit here. The diode is turned into a resistor, is replaced with a resistor. The current source here is, if you go through the calculations, it's going to be GMV pi. Now the question is that what is V pi? Or how do we define these? The important question here is that what is the direction of that current source, and then how do we define V pi here? So let's, for a moment, assume that I connect the emitter to ground, AC ground, and increase VBE, such as what we did here. We increased VBE in here in this circuit, and looked at what happened to IC and all that, right? So we increased the base voltage. Emitter was grounded. We increased the base voltage. We moved from the bias point here to slightly higher value, which gives us a larger AC current. So when you looked at the output here, IC was IC plus some little IC, okay? So let's see what happens here. If I assume the same thing, that IC here is a change in base voltage is going to give me a small signal quantity. So emitter is grounded, so it's VBE plus VBE. As you increase the base voltage, what happens? VEB will become smaller, right? The voltage drop across the diode that you have over there, V emitter is fixed, VB is increasing, so VEB is smaller. So when you look at the equation here, the current at the collector becomes smaller, right? So you increase the base voltage, the collector current goes down. It's the opposite of what happened for an NPN device. And it's obvious, in one case you're increasing VBE, in the other case you're decreasing it. So if I want to look at this equation here, if I want to keep all the directions the same and all that, then I will have a negative gain for IC, because when you increase VBE, IC will go down. IC, the total will go down. IC plus IC will go down. So therefore, in front of this IC here, you have a negative sign. It has to go down. It's as if the current is going backwards. Instead of flowing out of the collector, it's going backwards. The IC that you produce is going backwards. So the direction of the current that you put for this is GM. And we're talking about increasing VBE, V base with respect to the emitter. So if this is your base, this is your VBE. And then, this is going to be your RPi or RBE, whatever that you decided. But this is going to be the model for a PNP device. Well, just flip it over. And if you flip this over, this is what you have. It looks exactly the same as what you had for an NPN device. So here's the good news. Again, something that will make our lives a bit easier. That for small signal analysis, DC analysis, PNP and NPN are behaving differently. You use different equations, you take care of the currents and all that. But when it comes to small signal, the model is exactly the same. They behave exactly the same. So what that means is that you can make any circuit with an NPN transistor or a PNP transistor, and then as long as you keep them at under the same operating conditions, you get the same behavior from them. Negative gain, positive gain, all these things will be very, very similar. And then you go and choose the transistor that is available to you and make the amplifier using that transistor. So very convenient. It's actually very convenient. You take the PNP transistor out of your circuit, replace it with this model that I showed. I'll go through a couple of examples in a second, but let's just go through the steps that we need to take in order to do this analysis as we mentioned. So step one, do the DC analysis. Right? Go and figure out what your operating points are, where is the IC for your transistor. We saw that IC is the most important parameter that you need. So you need to figure IC. But at the same time, you need to check VCEs to make sure that your device is not saturated, right? So just do that part first. Always do the DC analysis first. Once you've done that aspect, and then that aspect is done without AC sources included. Just take out the AC sources. If it is a voltage source, AC voltage source, you replace it with a short circuit. If it is an AC current source, you replace it with an open circuit. Do your analysis at DC, and then once you're done, calculate the small signal parameters. For BJT circuits, this is GM and RPi for each one of the transistors. You may have a multi-transistor circuit, each one is biased at a different current, so you go and do the calculation for all of those. Then build the small signal model. So how do you do that? Well, you're done with the DC analysis. You go and take the DC sources out of your circuit, keeping in mind that you're now going to look at the changes, right? So take the DC sources out. Again, a voltage source becomes a short circuit. You're zeroing those sources. And a current source becomes an open circuit. And keep only the small signal sources in the circuit. Take the transistors out of your circuit and replace them with their small signal model. Good news here is that the small signal model for PNP and NPNs are the same. And you build this new circuit, and then you solve the circuit. It's a linear circuit now. hopefully it will take just a bit of time to solve it. It's usually the AC analysis, if you build it right, is usually simpler than the DC analysis. And then at the end of that story, if you want, you can go and say, okay, so my DC point was 2 volts, and now I have a gain of 100 for a 1 millivolt signal, so the signal goes up and down by about 100 millivolts around that 2 volt point, or you can just keep things separate as they are, right? So the DC and AC analysis part, you report them separately. This is the DC voltage, and this is my AC gain, or input resistance or output resistance, right? And these are the steps that you need to take.